Okay, so the question that we want to investigate today, or here's our first example. The goal is to find all solutions to the following differential equation. And the differential equation is y prime minus 2xy equals 1. Now notice that this differential equation is linear. It is first order, right? Because the highest order derivative is 1, is y prime, and is also non-homogeneous. So, in this case, as we talked about today in class, we've got 3 main steps that we're going to do. The first step is to find y1, which is our complementary solution. It's a solution to the complementary equation, and the complementary equation is just the homogeneous version of the original equation, right? So our original differential equation is y prime minus 2xy equals 1. So we just turn that into y prime minus 2xy equals 0. Step 2 is to find u, and u prime is equal to q over y1, and we'll talk about what q is later on. Q is essentially going to be 1. This 1 here is going to be q. And then step 3 is to put it all together, and we'll use this formula here, y equals u y1. So now to do step 1, remember step 1, what do we do in step 1? In step 1, we find y1, right, by solving the complementary equation, which is y prime minus 2xy equals 0. And I actually want to discuss 2 different methods for solving it. The first method is going to be the method that we did in class, which is to say if we've got this differential equation, y equals y prime minus 2xy equals 0. Okay, if we want to solve this, the first thing we do is we want to separate those variables. So we add 2xy to both sides. Then we divide both sides by y. And we have y prime equals 2x. Right? Now we're going to, we actually integrate. Right? So we rewrite the y prime over y as dy times 1 over y equals 2x dx. We write it in differential form. And then we integrate both sides of the equation. That gives us this equation right here. The integral of 1 over y dy equals the integral of 2x dx. From there, we take when we integrate the left-hand side, we get the natural log of y, of the absolute value of y. And when we integrate the right-hand side, we get x squared plus c, because the integral of 2x is x squared. Okay, then we exponentiate. So e to the natural log of absolute value of y is equal to e to x squared plus c. That's what we have in this line right here. Okay, and then e to the natural log of y, of course, the e in the natural log, right? Exponentiation and logs cancel our inverse operations, and they cancel each other out. So we're left with just the absolute value of y equals k times e to the x squared. And just as a reminder, how did we get the k? We can rewrite e to the x squared plus c as e to the x squared times e to a constant, right? And e to a constant is just going to be e to the x squared times that constant. And notice here that k has to be positive since k came from e to c, and the range of e to the x is positive numbers only. So that's how we get the absolute value of y equals, let's focus in on this. That's how we get the absolute value of y equals k times e to the x squared. Now to get rid of the absolute value sign, we just write y equals plus or minus k times e to the x squared. And if k is a positive number, then plus or minus k we can just rewrite as c times e to the x squared. Okay, so that's our final answer, y equals c e to the x squared. Now, let's talk about method 2. We're still solving the same equation, y prime minus 2xy equals 0. And the second method is kind of following theorem 2.1 in the textbook. So what it's doing is essentially skipping the details of method 1 and going straight to applying a formula. So here's what it says. It says if y prime plus p of xy equals 0, then the solution is, and let's write this a little easier here, the solution, a little neater, the solution is y equals a constant times e to the negative integral of p of x dx. And again, this is theorem 2.1.1 in the textbook. So the way we would apply this theorem is we would say, first of all, we've got to figure out p of x. Now look at this. Okay, so our equation is y prime minus 2xy equals 0. So that means that p of x, we can look here, p of x, what is p of x? It's going to be negative 2x, right? And we've got this written down here. So p of x is equal to negative 2x. And that means that our solution, right, y equals c times e to the negative integral p of x, is going to be y equals c times e to the negative 2x dx. Because remember, p of x is negative 2x. So the negatives cancel each other out, right? The negatives cancel each other out. So we just have the integral of 2x. And the integral of 2x is just going to be x squared. Okay? So we just get e to the x squared. And our solution, our general solution, ends up being y equals c times e to the x squared, which is exactly what we got from before. So I want to caution you that if you're going to use this this theorem 2.1.1 and just use the formula straight out, then when you are calculating this antiderivative, you don't need to add plus c because that is already accounted for in this coefficient out here in the front. Okay? There is no preference. Thank you. There's no preference between method 1 or method 2 because they give you the same answer, right? So if you prefer method 1 and that works for you, go for it. If you prefer method 2 and you want to memorize that formula and apply the formula, go for it. Okay, so we have found our answer here. In our answer, so step 1, which was to find y1. For y1, we want a solution, so we can choose y1 equal to, we can just let c equal to 1, e to the x squared. Now we're going to choose c equal to 1. So we'll just have y1 is e to the x squared. And you can choose any constant for c except for 0. Because if you choose y1 to be 0, then that means we're back to a trivial solution. And our solution to the entire equation, when we put it together, we'll just have y equals 0, which is not going to be a solution of our original differential equation. So let me, in fact, go here and modify this to say y1 needs to be a non-trivial solution to the complementary equation. Okay? So we can just work with y equals e to the x squared. Now let's do step 2, which is to find u. And u prime equals q over y1, and we're going to integrate to find u. Okay, so finding u. So looking at this here, u prime we said is equal to q over y1. Now, y1 we found in step 1, right? So we found y1 in step 1, and in fact, we were able to say definitively that we're going to choose y1 equal to e to the x squared. And q, you might have forgotten where we get q from. Remember, if this is our general format for our linear first order differential equation, y prime plus p of x times y equals q of x. That q of x is the numerator in y prime, in u prime, right? So that q refers to, do you see that? That q is this q in our numerator. Okay, so for us, what is q? Well, we need to look back at our original differential equation, and according to our differential equation, our p is negative 2x, p of x is negative 2x, and q is just going to be 1. So that's what we've gotten written down right here. So q of x is equal to 1. We plug this in. U prime is equal to 1, right, over e to the x squared. And we can just rewrite that, remember, as e to the negative x squared. Okay? Now, if we know that u prime is equal to e to the negative x squared, the question is, what is u? Well, the answer is u is going to be an antiderivative of e to the negative x squared. Remember or recall, we can't integrate e to the negative x squared. We could try to use power series, we can approximate it, but this is the closed form. So if you try integration by parts, it'll fail. If you try u substitution, it'll fail. There is no closed form. And you'll remember that from your Calculus 1 or Calculus 2. So basically what we have to say is u is equal to, and this is, we're using our fundamental theorem of calculus here, u, we're just going to write u as the integral from 0 to x of e to the negative t squared dt plus a constant. So this is it. This is our answer for u. We're ready to do step 3, which is to put it all together. So we know that y is equal to u times y1, right? So if y is equal to u times y1, u, we said, is this, weird looking integral plus a constant, and y1 is e to the x squared, right? So that's y1 is e to the x squared, and the u is this weird looking integral plus constant, plus a constant. Okay? And that's essentially it. So we can just rewrite this as, so we could, let me try to show you here. What we could do is we could try to simplify this by expanding. So I'm going to multiply, and I'll have e to the x squared times this integral, right, from 0 to x of e to the negative t squared dt, and then distribute it out. So I'll have plus c times e to the x squared. Okay, so that's how I get that second term. And then now for the first term, I can combine, right, if I've got this e to the x squared, it has nothing to do with t, so I can bring it on the inside. So I've got the integral of e to the x squared times e to the negative t squared. And I can use my powers of exponents to say e to the x squared minus t squared on the inside here, right? So this is my final answer for my solution, general solution to the differential equation y prime minus 2xy equals 1. Minus 2xy equals 1. Okie dokie. So that's our first example. For the second example, let's look here. So the second example is an initial value problem. So it is solve the initial value problem, y prime minus 2xy equals 1. Oh, wait a minute. That should look familiar, right? So look, this is exactly the same differential equation that we solved in the previous example. We have added an initial condition. Our initial condition is we want y of 0 to equal 3. Okay, and so IVP, just in case you're not sure, initial value problem. So that's the IVP. Okay, so we already know that our general solution to this differential equation, y prime minus 2xy equals 1, is right here. This is our general solution. We already know this. Oh, that was horrible. Um, Here we go. We can just say this is it. So we know this is our equation. So what we need to do is we need to find the value of C for which this equation satisfies y of 0 equals 3. Okay, so this is from our initial condition. Remember, our initial condition is y of 0 equals 3. So we need y of 0 to equal to 3. And now we're going to use the fact that we have a formula for y of x, right, to say what is y of 0. It's going to be the integral from 0 to 0, because everywhere we see x, replace it with 0, right? So if this is the formula for y of x, if the formula for y of x is here, then what is y of 0? Everywhere you see an x, replace it with 0. So we've got the integral from 0 to 0, e to the 0 squared minus t squared dt, plus c times e to the 0 squared. Now, let's see if we can actually try to clarify some of this. So the first thing we can notice is that what is e to the 0 squared? That's going to be equal to 1, right? Why? Because e to the 0 squared is e to the 0, which is 1. So all of this is going to be c times 1, which is just going to be c, right? Now what about this first summand? What is the integral from 0 to 0? What does that even mean? Well, remember from calculus that the integral from a to a of f of x dx is equal to 0 if f is continuous, because this is representing area, and the area from a to a is just equal to 0. So this first summand, all of this is just a fancy way of writing 0. So what do we have? We'll have 0 plus c. So c equals y of 0, right? And y of 0 equals 3. So it must be that we need c to equal 3. So we plug in c equals 3 into our general solution, right? So instead of c, we'll have 3. And this is how we get the solution to that initial value problem, right? So that used to be c, but now it is 3. Okie dokie. There we go. Thank you.